All right, everyone, welcome back. Today we're going to be discussing some more differential geometry, and in particular, we're going to be looking at equiareal and conformal maps and more on the first fundamental form. So, to begin, we're going to look at this rather large proposition. I'm not going to prove any of it, but most of it is fairly straightforward. So, we're going to start with map G is if G is inner product preserving, then G of x and G of y, the inner product, is equal to the inner product of x and y. So, sorry, these are linear transformation. G is a linear transformation in this case. Furthermore, we have that the norm of G of x is going to be equal to x, the norm of x. Furthermore, matrix of G, which we'll call A, is orthogonal. Actually, you know what? First, G is a map from V to W, and both are subspaces of R3, so let's just get that out of the way. And furthermore, the basis of W, the range, the range vector space, can be chosen in such a way such that A is the identity matrix. Now, the proofs of all of these require some linear algebra, so I'm not going to go through all of that, but these are results that we will just take for granted. So now let's discuss if G is area preserving. Then we have that, since we're working in R3, we can discuss the cross product, and we have that the cross product of G of x and G of y. The norm of that is equal to the norm of the cross product of x and y. Furthermore, the I believe area distortion area distortion of G is equal to 1. The determinant of the matrix A is going to be equal to either plus or minus 1. And finally, let's number these. So the bases of V and W can be chosen in such a way that the matrix will be equal to this for some positive lambda. Now, if G is angle preserving, then the angle between G of x and G of y, those vectors, is going to be equal to the angle between x and y. there exists some positive lambda such that the inner product of g of x and g of y is equal to lambda squared times the inner product of x and y for all x and y in V. And from there, it shortly follows that there's a similar thing with the norm. Furthermore, we have that A is a scalar multiple of an orthogonal matrix. Furthermore, the basis of W can be chosen in such a way that A is equal to lambda 0, 0 lambda for some positive lambda. And finally, there exists an orthogonal pair of non-zero vectors x and y in V such that g of x and g of y is orthogonal, and that following equation holds. So now that we covered all that, let's discuss equiareal and conformal maps proper now. Suppose S1 and S2 are regular surfaces. So we say that a diffeomorphism F from S1 to S2 is called equiareal if for all P in S1, the area distortion equals 1. And furthermore, we have that a diffeomorphism F is equiareal if and only if given a polygonal region R, area of R is equal to area of f of R. So what we can use to help prove this proposition is the fact that if we have a polygonal region R, then we can calculate the area of f of R as the double integral over R of the area distortion df dA. And since if a diffeomorphism is equiareal, then the area distortion of its derivative is going to be equal to 1, then this becomes 1, and we're just simply integrating over R, and that's just going to be R from simple properties of multivariable calculus. So now let's discuss an equiareal map that came from the famous mathematician Archimedes, actually. So we are examining a function f from the sphere with a couple points removed, mainly the top and the bottom, and it maps to the cylinder. The cylinder we define to be the points x, y, z in R3 such that x squared plus y squared equals 1 and negative 1 is less than z is less than 1. So what that looks like is, so we have our sphere, but the top point and the bottom point is removed. And we're mapping it to cylinder. So maybe let's okay. We can actually discuss this map explicitly. For if we have x, y, z, then we have so what will this look like? Like we've discussed the surfaces here, but if you think about it, we have a cylinder and you can think of the sphere as being inside the cylinder. So this is my very poor rendition of it. And of course, the top and bottom points are not here. And what we're doing is, this point maps to this point, so we're good. This point maps to this point. And we're basically sort of doing something like this. And then, of course, we're doing it in 3 dimensions as well. So this goes. It's something like that. And we claim that this function, we'll call this Archimedes' theorem. Why did it do that? F is equiareal. So now what we can do is we can discuss, we just have to show that the area distortion is equal to 1. So first, let's consider the coordinate chart sigma. where we have this is basically just like the standard spherical coordinate stuff with distance being set to 1, of course. So let's suppose that, now you can see this doesn't cover the whole sphere first, but we can easily cover the sphere using an identical coordinate chart just in the opposite direction. So let's say we have that a point Q, we have a point Q, and P equals sigma of Q. So P is on the sphere. What we can do is we can take the partial derivative of sigma with respect to theta, and we get, let's see if I can not mess this up, negative sine phi, or phi, sine theta, sine phi cosine theta, and then 0. Then we have sigma phi, which is going to be equal to cosine phi cosine theta, cosine phi sine theta, negative sine phi. And now if we take the cross product of that, okay. We get, you know what, I'm just going to skip to the end result because I'm kind of lazy. So, with this knowledge, we can compute the area distortion to some degree at a point P. But remember, this bottom denominator is sine phi. So all we need to do is show that the numerator is also equal to sine phi, and then we're done. So here's what we do. Let's consider the surface patch for the cylinder, which simply becomes, if you do the calculations, cosine theta, or sine theta, oh, that's sine theta cosine phi. Now, we have that by the chain rule, the partial derivative of tilde sigma with respect to theta is going to be equal to the derivative of f at the point P of sigma, the partial derivative of sigma with respect to theta, and similar for phi. So that's going to be, so we have dfp sigma theta times dfp sigma phi is equal to this. Let me scroll down, which is equal to the norm of the cross product of negative sine theta cosine theta 0 times 0, 0, negative sign phi, which you can do the calculations, is going to be equal to sine of phi. And therefore, this is also sine of phi, which equals 1. And that completes our proof. Okay, so now we're going to talk about conformal maps. So let's say that we have S1 and S2 regular surfaces, and we have a diffeomorphism, F from S1 to S2. We say it is conformal if it preserves angles. So the angle between x and y is equal to the angle between dfp of x and dfp of y, where p is in S1 and x and y are in the tangent plane of S1. So this definition is pretty tough to work with, but luckily there's a proposition we can use that allows us to identify conformal maps easier. So diffeomorphism is conformal if we have that the inner product of dfpx, dfpy at f of p is equal to lambda p squared times the inner product of x and y at the point p for all p in S1 and x, y in the tangent plane of S1. And you might be asking, why is that? It is a direct corollary of the fact that if G is angle preserving, then we have this, which implies this. And the vector spaces we're working in, instead of V and W, are the tangent plane of S1 and the tangent plane of S2 at P and F of P respectively. Now, because the tangent plane at one point may be different from the tangent plane at another point, lambda is not necessarily constant for all of the same points, but it depends on the point. So it's going to be constant with respect to the tangent plane vector space, but if we're taking it may depend on the point, is what I'm saying in S1. So now let's talk about, oh, that is bad handwriting. A stereographic projection. So basically what it does is we have a sphere and we have a plane sitting just below it. Sometimes the plane is cutting through the middle of the sphere, but TAP does it this way, so that's how we're going to do it. We basically map each point in the sphere to a point on the plane like so. So for this point, we take the line going through both of these points, since 2 points define a line, and see where it intersects the plane. In that case, it intersects it right here. How about over here? Maybe it'll be over here. How about over here? Maybe it'll be over here. And then over here, it'll be probably way out there. Notice that every point on the sphere gets mapped to a point on the plane except the North Pole. Now, I propose this stereographic projection is conformal. This is an example of a conformal mapping that preserves angles, but I'm not going to prove it because I'm kind of lazy. Now, we have that one final proposition is that if we have a diffeomorphism, f from S1 to S2, it is an isometry if and only if it is equiareal and conformal, so it has to be both. Now, the way we can do this is we can see that you can use the qualities of here. You can probably pick some of them. And then you can use the qualities of here. Angle preserving and area preserving must imply inner product preserving. And that's basically how you can do that. But I'm just going to move on to a little bit more about the first fundamental form. So let's go over a little bit of notation. We already know surface patch sigma, the notation for that, and its partial derivatives. So let's say that we have sigma as a function of u and v. Then we define the following. We define E to be the norm of the partial derivative of sigma with respect to u squared. We define F to be the inner product, like so. And then we define G to be sigma v squared. So to move forward and discuss about the first fundamental form, we're going to discuss some lemmas. So if we have a point x equals AB and y equals CD, and they're all in R2, then derivative sigma q x and sigma q y at p, or let's make sure p equals sigma of q, that equals the following. Oh. And then that quickly becomes the properties of inner products. So that's our first lemma. Then we have x equals AB, then the derivative of sigma at q of x squared at p is going to be a squared e plus 2abf plus b squared g. Then, if we have a regular curve, gamma, from 0 to L to U, where U is the domain of our surface patch, and gamma of t equals U of t, V of t, then the arc length, let's just denote the arc length, of the curve's image on the surface is going to be equal to the following. So this is going to be a really long expression. Oh, this is squared. And then 4, if we have a polygonal region R in V, where let's just make that clear. Then the area of R, which is on the surface, is equal to the double integral of the pre-image of the surface, a square root EG minus F squared dA. And from these lemmas, it is clear that we can develop the first fundamental form in local coordinates, like so. We define it like E du squared plus 2F du dV plus G dV squared, where E, F, and G are defined before. Now, what the du and dV mean is beyond it sort of is beyond the scope of these lectures. We'll learn about things called differential forms later on, but yeah, maybe if I continue this series into more graduate level stuff, I'll cover differential forms substantially. So thank you for watching, and I'll see you in the next video.